So hi, my name is Colleen Bertoni. I'm in the performance engineering group at ALCF. So in this presentation, we're going to talk about some topics related to using Openmp efficiently on Theta GPU. But before we go into that, I usually like quickly reminding everyone like what we're after. So this talk is supposed to be about using Theta GPU efficiently, and so what do I mean by that? One way to think about this is in terms of the upper bound on how fast you can compute. So upper bounds are nice, since once you have an upper bound, you can try to understand where you are in relation to it and figure out what you need to change or do to hit the upper bound. So then the question is where to get the upper bound. And at a general level, the maximum speed at which you can do work is typically how many cycles per second per core times number of cores times how many operations each core can do per cycle. So you don't typically have control over the clock rate, but you do usually have control over how well you use all of the cores and how well you're having each core issue instructions per cycle. There's also other bounds in terms of memory bandwidth and cache, but just to keep things simple, this is what we'll focus on for this. So like you know from the previous talks for Theta GPU, we have an additional complicating factor, which is that the nodes are heterogeneous. So we have a CPU and a GPU just shown simply in the right-hand upper corner. So we need to consider both the CPU and the GPU when we're thinking about programming. So just to make it concrete, so on Theta GPU, we can compute these upper bounds like this, once for the GPU and once for the CPU. So for the GPU, like we talked about before, they're NVIDIA A100. So we multiply the frequency by the number of cores, which is the number of SMs or streaming multiprocessors per GPU times the 8100 GPUs. This is per node. And then each of them can compute 32 double precision floating point operations per core per cycle. And then that gets multiplied by 2, since this instruction can be a multiply and an add at the same time. So that's the GPU portion. And then for CPU portion, you can do the same thing. So for the 2 AMD EPYC CPUs, about 2 gigahertz times the number of cores, which is 64 per CPU, times the number of double precision floating point operations per core per cycle, and then multiply by 2, since this instruction could be a multiply and an add at the same time, and then multiply by the width of the, like how many things you can do at once with the vector registers. So 4, since we have 256 bits, so you get the 4. So I know that, yeah, was a lot to get the maximum speed, but the reason I wanted to show that was just to make it really concrete that this makes it really clear that there's way more computational power on the GPUs than the CPUs, like over a factor of over 10x. So if you have a lot of compute, you really want to make sure you're running on the GPU instead of the CPU. So that's shown in red. But there are other bottlenecks to think about besides compute power, so memory bandwidth. But the one I wanted to call out, because we'll talk about using it with Openmp, is to be careful about data transfer bottlenecks. So you have a CPU and a GPU and a connection between them. So it's important to note that the transfer of data between a CPU and a GPU is about an order of magnitude slower than accessing memory or data from memory on the device. So that was, yeah, so the agenda, so that was just background for things to think about in terms of the hardware when you're running on Theta GPU. And so the agenda for the rest of the talk is really how Openmp can help you in getting closer to the upper bound. So for the rest of the talk, we'll focus on how to use Openmp, in particular to use it to target the GPUs, just to make sure you are running on the area with the most computational power. So I'll give like maybe approximately 30-minute talk with slides, and then switch to, I'll share the rest of my screen and do a demo of using Openmp on Theta GPU to target the GPUs. So this will kind of be a Openmp 101 plus some basics. So I think there might be some people who already know a bunch about Openmp offload, but I wanted to just go through the basics to make sure everyone's on the same page. And then if we have time left, we'll do some Q&A. So this is, I'll come back to this later for the demo, but if you want to grab what we're going to go through ahead of time, it's on the GitHub that Ray and other people pointed out before in the 01 Openmp folder. Okay, so we'll start with the Openmp offload, just overview. So why Openmp? So Openmp stands for Open Multiprocessing. It's an open standard for parallel programming, an API and environment variables that a lot of different vendors have implementations of. So the standard document, the specification document, is fairly large. A main reason for this is that the Openmp specification is it's very broad and expressive. It can express parallelism to target CPUs, CPU threads running on a multi-core system, but it can also target GPUs and accelerators, and also has some specific directives for vector or SIMD units. The vendors behind the new supercomputers at NERSC, Oak Ridge, and Argonne, so Perlmutter, Frontier, and Aurora will all also have Openmp compilers or runtime. So Openmp is fairly portable, so it will be supported on all of those systems. So just speaking of that, there are some resources of how to use Openmp across the different platforms and vendors. This is just a quick slide with the flags for how you can target different GPUs. So you can see sort of quickly that the most compilers that target hardware is for NVIDIA. This is mostly because NVIDIA has just been around the longest, but there are also compilers to target Intel GPUs as well as AMD GPUs. These are just the flags that work right now. If you want more information, you can see the link at the bottom. So I think that will be a much more comprehensive list. Okay, so I just wanted to cover some basic offloading topics to give people a feel for offloading before showing it during the demo. So like I talked about earlier, for systems with GPUs, like 90% of the computational power and bandwidth are on the GPU, so running on the GPU is essential. And the goal is to transfer data and execution control from the CPU to the GPU so we can run code on the GPU. And of course, yeah, the thing I wanted to mention is that you don't need to use CUDA or other programming models for GPUs. If you're already familiar with using Openmp for CPUs, you can use it for GPUs as well. And just the list of compilers supporting offloading are in the bottom of the slide as well. Okay, so let's say you already went through all the work to parallelize your code for CPUs. So here's just a really simple example that computes Pi for CPUs. So with the standard Pragma OMP parallel 4, which spawns threads on a thread team and distributes iterations of this loop to the different threads. But now all the new systems, like we talked about before, are using GPUs and have accelerators. The nice thing with Openmp is that you can take advantage of the work you did to parallelize with Openmp, at least as a starting point, to run on GPUs with Openmp offload. So even with running on CPU, you've already done the work to identify which loops or which parts of your application can be run in parallel. So you can, at least as a beginning start to use GPUs or start to use Openmp offload to run on the GPUs just as a first getting started. So if you want to run the GPU, you switch from parallel 4 to target team distribute parallel 4, like just as shown here, going back and forth. So one question you might have is why there are the additional different pragma that we have for Openmp offloading. So to motivate and explain some of the target offload terminology, I'm going to go through target teams in parallel quickly. Okay, so part of this is that it has to do with how these different terms map to the hardware, where the hardware is GPUs. So we normally think about GPUs as to some extent having hardware hierarchies, and we can use NVIDIA hardware as an example since that's what we're running on today. So I know a lot of people are familiar with GPUs and probably already know all this, but I just wanted to repeat it just to make sure everyone's on the same page. And Scott's example of talking about Intel hardware is very similar to this. So GPUs tend to be built out of the smaller, repeated, scalable units, and that's true across vendors. So like Scott said, with Intel, it's repeated subslices or slices. AMD has repeated dual compute units, and NVIDIA has repeated streaming multiprocessors. This is important because in the smaller independent units, there are usually shared resources that aren't shared outside of the unit. So like local memory or hardware to synchronize. So the GPU is composed of a bunch of the smaller units all bundled together, and they probably share some resources like main memory, but not all of the resources, like maybe hardware to synchronize inside of a unit, but not between two different units. So that defines different levels of hierarchical parallelism, where the different levels are based on what resources are shared at that level. So fine-grained parallelism is inside of the unit, and coarse-grained parallelism between the different blocks. So in Openmp on NVIDIA hardware, the parallel construct, which was using the fork-to-run parallelism, maps to fine-grained parallelism, running on only one of the little units. And then coarse-grained parallelism comes from running from an Openmp using the teams construct, which runs across all teams across all of the GPUs. So as background, we can go through the different constructs. So the target construct is the construct that just says, take any code that's inside of the region and run it on the GPU with a single thread. It also transfers data with some implicit and explicit rules, but we'll talk about that later. So the main thing is just to keep in mind that target takes code, switches execution control from the CPU to the GPU, and then runs on the GPU in serial. But serial isn't actually what we want. We want to run more threads. So then the teams construct that creates a team of threads running across the different smaller subblocks, or SMs in NVIDIA terminology. Each team actually only has one active thread that are running concurrently. This is the coarse-grained parallelism that I talked about before. And then the parallel construct creates threads in the team which can do things like synchronize with each other. And this is the fine-grained parallelism. So those are explanations for the different constructs. And when we put it back together and look at the example, we have the target teams parallel 4. And it's also recommended to include SIMD at the end of this. This has to do with, so a lot of compilers will just ignore that, but some compilers like the HPE Cray compiler needs to have SIMD at the end so that parallelism is expressed. So best practice is to include SIMD for now. Okay, so that's just a quick overview. So the stuff I talked about is stuff that you can work today with basically every compiler and most of the hardwares. There are some other features that are newer in Openmp from the 5.0 standards and on. And most of these are working today, but maybe won't work with every compiler yet. So the ones I wanted to highlight are in red. One important one is unified shared memory support. This means that the map clause would no longer be necessary. So it makes offloading GPUs a little bit easier because you don't have to worry about transferring data. Another one to mention is the loop construct. This can be used in place of the teams review parallel 4. And again, it simplifies expressing parallelism, but not every compiler has a really good implementation of that yet. The NVIDIA compiler does, which is one good one to use on NVIDIA hardware. So feel free to try that, but for the rest of the examples, I'll be using target teams distributed parallel 4, just because that seems to work across all of the compilers. So this is just some stuff to be excited about in the future. Okay, so just one other short topic before going to the demo. I wanted to talk quickly about data transfer. Again, this is really important because it's much slower to access memory across PCIe than directly in memory, like on a CPU or on a GPU. So data transfer from CPU to GPU and vice versa is much slower than accessing data directly in memory. So the target construct itself has implicit rules for mapping data, but it's mostly recommended to explicitly note the data mapping with the map clause. So here, the target team is distributed parallel 4 again, and the map clause, so this says to map arrays A and B 2 from the CPU to the GPU, so 2, and array A back from the device. So A is 2 from and B is just 2, just sort of shown in the little picture, map A and B post to device, and A, this should just be B back to the device. However, so the one issue with this style of offloading is that it ties the data transfer to the execution control. So when you hit the kernel, you do both switch from CPU to GPU and you move data back and forth. So there's, as we'll sort of see in the demo, that can be a problem sometimes. So of course, Openmp has a way of getting around that. It's with the unstructured data clauses. So that's shown here. The pragma OMP target enter data map to this does the mapping without also being tied to execution control. So the data moves to the device. Then there's a offload region. And then whenever you hit the target exit data, there's another data transfer. Even though this map is here, it doesn't do data transfer because Openmp does reference counting. So it knows we've already moved A to the device. So it stays there. Okay, so that was just a really short overview of Openmp and Openmp offloading. So I guess that took way less than 30 minutes, but that's okay. So now I'll switch really quickly to do a demo of Openmp on Theta GPU. And then if there's more time, which there might be, we can do a Q&A. And this is just some resources if you want. And I'm gonna change screen sharing. Oh, okay, can you see my terminal windows?
Yes.
Okay, thanks. Okay, so I'll be going, let me start that. I will be going through the Openmp offload examples from GitHub. So I already git cloned this. And I have the README open on the left. Is this big enough for everyone? Okay, I'll take silence as it's okay. So let me cd into the directory. So the left-hand side has the README for that section. And then the right-hand side, I just opened an interactive job. Oops. And interactive job, and I'll just go through this. So basically, I'll just be going through the README slowly, and we'll look at code examples as we go. So I got an interactive job, and I'll be going through 5 examples, going through the offloading, expressing parallelism, and mapping data that I talked about. And there are Fortran and C++ examples. I'll show both the code for both of them, but just for the sake of time, I'll go through, I'll compile and run the C++ ones, but if you want, we can go back and look at the Fortran ones too. Okay, so the first example I wanted to look at is just the most basic thing you can do, which is offloading code to the device with the target construct and getting device information from Openmp. So the C++ version is on the right, Fortran is on the left. So in both cases, we can use the routine OMP get num devices to ask the Openmp runtime how many GPU or devices it can see that we can run on. And then, like we talked about before, there's a pragma OMP target clause. So a thread on the CPU is running along until it hits the OMP target. then it stops and waits while the code inside the target region executes on the GPU. So all we have in here is a print statement saying if we are not on the initial device, print hello from the accelerator, otherwise hello from the host. So initial device is the host. So if we're on a GPU, it should print hello world from the accelerator, and otherwise print hello world from the host. And then the same in Fortran, except that you can see that Fortran has slightly different ways of marking that as Openmp, and it also has an end, say the name of the end of the target clause, because Fortran does not have curly braces like C does. But otherwise, the code looks very similar. Okay, so let's compile and run this. So make O1 target construct. And this is, we're using LLVM to run the C code, and then the NVIDIA compilers for Fortran, just to show different compilers from different vendors will run on the NVIDIA hardware. So for Fortran, instead of loading LLVM, if you wanted to try, you could load the NVHPC-no-MPI version. Okay, so let's run this. Target construct. Okay, so it sees one device and says hello world from the accelerator, which makes sense, that's what we expect. Oh, but sometimes it's nice to be able to check that what Openmp tells us is correct. So we can use NVIDIA tools for this since we're on Theta GPU. So the one that's useful here is NVIDIA SMI. This just tells us NVIDIA's tools reporting how many GPUs there are. So here we see one NVIDIA A100, which makes sense. So we did have one GPU, so that's good. The other one that's useful is Insight Systems. This is basically formerly MVProf, if you are familiar with it. It can do simple profiling for you, like the thing that, maybe the most important thing is just checking that your code ran on the GPU, and you can also get an overall sense of data transfer. So I think the simplest way to use Insight Systems is nsys mvprof one target construct, so we can just run that with what we ran. So you can see it prints API timings, and then maybe the more important part for here is the time spent in the offloading kernel. So we see the Openmp offloaded region. The name is mangled, but it gives you the function you're running in and the line number. It also tells you about data transfer, and that will come up in one of the next examples. Okay, the other thing about showing this is Openmp is always built on top of some other programming model. So for example, Openmp for NVIDIA is built on top of CUDA, but that basically means that any tool from that vendor will also work with Openmp because it's just sitting on top of the lower level language. So it's sitting on top of CUDA, so you can still use NVIDIA tools to get information about Openmp offload out of it. Okay, so that was the simplest thing you can do. And like we mentioned before, that only spawns one thread on the GPU, so it's not really taking advantage of all the resources available on the GPU. So the next example looks at spawning more threads. So that's 0 to target team is parallel. So you can see this is just a loop over 10,000. The target team is parallel for SIMD. And the only thing that's happening inside of this loop is it's printing which thread out of how many total threads and which team out of how many teams is printing for whatever index. So this is super basic. It just shows that the iterations are split between the teams and threads. Yeah, it's really basic, but I really like seeing things like this just to sort of be sure that iterations are actually being split among threads and to show that we are being split into teams with a different number of threads in the teams. And then the same thing for Fortran, target teams distribute parallel do SIMD and printing the same things. Okay, so let's go back to the terminal. and build this. Teams. Okay, so compiled it, and then we can run it. So yeah, we get a bunch of output because we are running over a loop of like 10,000. But what we can see is which thread, so thread, for example, thread 86 out of 128 threads, and a specific team out of how many total teams and which index it's using. So here we can see that this device was using 79 teams and it had 128 threads per team, just by default. However, we can control how many threads and teams are activated with some clauses in Openmp. So just to show that, you can change this example to add num teams, just say 2, and thread limit. So this shows that we're asking it to spawn 2 teams and 2 threads in each team. If you're familiar with CUDA, this is basically the same as in that triple chevron notation, num blocks and block size. So we can compile this again. Go to and then rerun this. Yeah, and here we see threads and teams. So this is just showing that you can control how many teams you have and how many threads you have. Okay, so we checked that we could execute code on the device and that we're spawning threads and can run in parallel. But to do any actual work, we need to be able to transfer data to and from the device so that it has something to compute on. So that's where the last thing I talked about, the map clause, and then the last couple of examples come from. So yeah, so like, yeah, left is Fortran, right is C. So this is a really simple example, just doing vector addition, basically the HPC hello world. So we have arrays A and B. We want to multiply B by a scalar and then add it to A and then restore it in A. So there's just this loop that runs over the elements of A and B, adding them together. So in CPU land, we would have put bracket Openmp parallel 4 or parallel do for Fortran on this loop. But since we want to run it on the GPU, we put target team distribute parallel 4. And we want to transfer A to and from the GPU. So we use map to from. And we want to map B to the device, to the GPU, but we don't need it back because we're just using it to compute on the device. We're not actually modifying it the way that B is. So one thing you can note is in C, we actually need to specify the length of the array that we're passing. But in Fortran, we don't. This is because with Fortran, if we use allocatable arrays, it stores the length that's associated with that array. So when we do map, when we map the array, we don't need to say the length for Fortran. So Fortran for the win for this mapping data. And then after doing that computation, we just do some error checking. So then let's compile and run this. And then we run O3 map. Okay, so it prints success. That's good. So we're getting the correct answer. But we were interested in looking at the memory transfer. So we can use Insight Systems again to look at this. And here I'm going to use the print GPU trace flag. And this is nice because it gives you, I'm just going to make this bigger and cut out some of the middle, just so it's easier to see. But this is nice because it gives you a timeline of what's happening. So you have timestamps and what's happening at each time. So this is nice because you can see, for instance, you can see that offload region here, again, the function name and the line number. And then before that, you see 2 memory copies from host to device, and they're each 0.008 megabytes, which is about 8 kilobytes. And then you have offload region, and then a device to host transfer also of 8 kilobytes. And if we look back at the code, we're transferring A and B to the device, and then just A back from the device. And the size of A and B is 8, or they're doubles, so the size is 8 bytes. And then we're transferring 1024 of them, so it's 8 kilobytes, so that the size makes sense. So this is nice because it checks that what we're doing in the code matches what the profile is telling us, that we're taking 2 8 kilobyte transfers from host to device. We do a kernel that works on them, and then we transfer, do another data transfer from device to host after that. Okay, so now let me make this smaller again, and then a slightly more complicated example. Okay, so this just builds on the previous one. So let's say we have multiple arrays A, B, and C, and we want to call a function called scaled vector addition, which is a function that's often called DAXB on them. And so like good programmers, since we want to use the same code block multiple times, we take it and write a function, DAXB here. This is the same as before. We were taking one array, scaling it by something, and then adding it back to that array. So the same sort of code as before, but we put it in a function and we call it twice on 2 different sets of arrays. So first take B, multiply by the scalar, add it to A, and then take A, multiply by the scalar, and add it to C. And we want this to run on the GPU. So again, we're still using Openmp target teams distribute parallel 470 with the same data mapping as before. Okay, so let's compile and run this. And yeah, I'm still just following the README. So let's compile it. Compiled it, and then we run it, so success, so it's working. But now let's look at the data transfer like we did before. So nsys mvprof. Okay, so we're running it, and we get the same sort of trace output, and I'm just gonna remove the middle part just to make this easier to see. Okay, so this is basically similar to what we have before, where we have the two calls where we have function name and line number. So we call that twice. Before each call, we have 2 8 kilobyte transfers from host to device, and then offloading region, then a transfer from device to host, then the next 2 host to device transfers, offloading region, and then device to host. Again, yeah, this is what we expect because we call the DAXB routine twice, and we have, with each routine, we have transferring A and B from host to device, offload region, and then A back from device to host. Okay, but which makes sense based off of the profile we have, so that's good. But if we look at the code, do we actually need all of this data transfer? So for sure, we need A and B to be transferred to the device for this first call to DAXB, but at the end of the first call, we send A back to the host from the device, and then we just send it to the device again, because A is sent back from device to host, and then here back from host to device. So we could have just left that on the device the whole time. So there's actually no need for data transfer between the two kernel calls. So the issue here is that the data transfer is tied to the kernel launch. But like I mentioned before, and like in particular this code here, it's really useful to split the data transfer and the kernel launch up. So leave the data on the device until you need it. And that's really just a general GPU optimization, not really specific to Openmp, because data transfer is quite expensive, or relatively expensive. Okay, so the last example is doing this in Openmp with the unstructured data constructs that I mentioned before. So that's this example. Okay, so basically the same code as before, but we've added target enter data map for A, B, and C, and same thing for Fortran, target enter data map A, B, and C before the two calls to DAXB. And we left you can remove the map if you want it up here, but we left it in, and Openmp won't retransfer it again, because it does, Openmp is doing reference counting, so it knows if the arrays are on the device or not. So it won't retransfer it. So let's compile this. Oh, and yeah, the other thing to mention, yeah, so there's target enter data to move the arrays to the device and leave them there, and then update from, or you could do target exit data to move it back from the device to the host. So let's compile this. Structured function. So it compiles. And it runs correctly, that's good. And then we can look at the data transfer again. And says mvprof. Trace. Okay, and like, I'm gonna remove middle part. Okay, so this is what we ended up with. We have here 3 8 kilobyte or 0.008 megabyte transfers from host to device. So that matches with the 3 target enter datas. Then 2 calls to the offload region, so 2 calls to DAXB. And then finally, 1 transfer from device to host, from the target update from, moving C back from device to host. And this is exactly what we expect. So doing the same work, but no data transfer in between the 2 offload regions. So this was just a quick using Openmp, or how to use Openmp to get rid of extra data transfer if you don't want it with every single kernel call. So this is all that I have for the demo.